All right, so we finished up 9.1, and today we're going to start 9.2, right? And then tomorrow we'll have our quiz on 9.1. I'll post it on ELC right after class. All right, but when we talked about sequences, what we said was that, right, that was an ordered list of terms, right? And those terms had to be written in a certain order because they had a pattern associated with them, and if we did not write them in the right order, we would violate the pattern, right? And we ended class on Thursday by looking at how to write the actual equation when we actually saw the list of terms, right? And then we know that if we've given the equation, we can just come up with the list of terms by plugging in our n values. So series, which is what we'll spend most of the unit on, series are the sum of sequences. So rather than just individually listing out the list of terms, we're actually going to add up every single one of the terms on that list. And just like sequences were infinite sequences, right, when we went all the way to infinity, we're literally going to be adding up infinitely many things, okay? And so sometimes we're going to see that you can add up infinitely many things and you get a finite sum. And then sometimes we can see, for obvious reasons, when you add up too many things, they're going to add up to infinity. So, excuse me. So we're still going to have the concept of convergence and divergence. It's just it's going to converge when we get a finite sum, and we're going to see it diverges when it does not. Right? So the form of a series, the general form, is we're going to use sigma, right? And sigma is what you use when you want to add up a bunch of discrete things, right? We used integrals when we wanted to add up continuous things, right? So when we were calculating area under the curve. So there will be some term that we will be familiar with. And you start at the bottom here. This is telling you what index number to start with. So sometimes this could be 0, 1, 2, right? So whatever value in this is, that's where you beginning plugging in for n. We only use whole number integers, and so we would see we would have the first term, right, the second term, the third term, and we would continue all the way to infinity. Now, in order to test a series for convergence, one thing has to always be true, okay? So we're going to write this down and then I'll explain what it means, right? So an infinite series right, so this is an infinite series will only converge, right? I mean, we can add all these numbers up to a finite number if the sequence that generated the series converges to 0. So this kind of intuitively should make a lot of sense because we said that when a sequence converges to a value, what happens is eventually out and down the line as you get to infinity, every number on the list just becomes that number, right? So if we had the sequence 1 over n, we saw the fractions were getting smaller and smaller and smaller, and then eventually we would just have 0, 0, 0, 0, 0, 0, infinite number of zeros. So if you're adding up a list of infinitely many things, and the end of the list doesn't turn into 0, well then it sort of has to add up to infinity, right? So imagine a sequence that's just the number 1, right? So just 1, 1, 1, 1, 1, 1, 1. Well, if you try to add that list up, well, that's just like counting to infinity, like every kid likes to do, right? 1, then you get 2, then you get 3, then you get 4, then you get 5, right? You're eventually going to hit infinity. So if the end of the list does not turn into 0, the only way you can capture a finite sum is you need all those zeros at the end, so you're just not adding anything new to the pile, right? So one of the things, just like I told you guys when we did integrals about you should always check for U substitution, right, at the beginning of a problem, because It's the easy way to integrate. You should always verify when we're asking you about convergence or divergence of a series, does the limit of the term go to 0? Because if the limit of that term does not go to 0, well then it's going to diverge by default. Okay? So it's just an easy question to ask at the beginning of the problem. You guys, we've been doing enough with limits and we're going to do a lot more with limits. You should be able to sometimes just eyeball those things and tell. And if you can say, oh, that doesn't go to 0, you get to shut the whole problem down because it's by default going to add up to infinity. Okay? So let's look at how we figure out what a series could sum to. So if you want to figure out what a series sums to, because we're doing infinitely many terms, well, with sequences, right, we had a pattern and we could look at the nth limit. So to sum a series, so when we look at a new series we've never seen before, and we don't really know any of our obvious tells yet, but we have some clues on whether or not we can determine if it diverges or converges. But once we're pretty sure that a series converges, and we want to know, well, can we actually calculate what the exact sum of it is? So one of the things we do is we look at the series of partial sums. All right, so here's what a partial sum would look like. S stands for sum. And we would say, well, S1 is simply the first term. If I wanted to know what the second partial sum is, S2 is saying add up the first two terms. S3, right, would be add up the first two terms. And then the nth partial sum is saying to add up the first n terms. So what each of these values are doing for us is they create their own sequence. It's a list of ordered things, right? And by looking if there's any patterns in those partial sums, we might actually be able to generate a formula that we can say, oh, well, if I'm summing this sum from here to, or the series from here to here, I can put it in my formula and I can actually tell you what everything sums up to. So what we say, and we're actually going to play around with some of this stuff in a minute, right? If the sequence of partial sums converges to some value S, then we say the series converges. If we see that the partial sums diverge, then we say that the series diverges. So I want to start off by looking at her old friend, 1 over 2 to the n. Told you I spent a lot of time with him. So I want to look at this sequence, or excuse me, series. We're going to start at 1 to infinity. So we know that this is, if we're starting at 1, right? 1 over 2 to the 1 is going to be 2. So we're basically looking at this. Now, I actually know that this converges, right? We know the sequence converges. In addition, we know the series converges, right? And if you do that test we said, we'll look at the a sub nth term, right? 1 over 2 to the n. We know the limit of that is in fact 0. So the limit of this being 0 doesn't guarantee convergence. It just means you have a shot at it. Okay? So this does in fact converge. The sum of all these numbers actually converge. And not only do they converge, we actually know that they sum up to a finite value. So the sum of this sequence is 1. And the reason I always like to start off with this one is there are multiple really neat ways I can prove to you that this is actually 1, okay? So the first is we can do it geometrically, just with a picture. Promise, I am really getting better. So, since we just had a big game this weekend, so my dad called me one day, this happened a few years back, and he was not into college football. He was an NFL guy growing up, and then when I sort of got into school and football, he got into football. So he started watching games. He would call me on Saturdays so we could talk about it and stuff, and I wish I could remember which teams were playing. But anyway, we were watching a game, and it was just like the craziest stuff we'd ever seen happen in the red zone. It was just personal foul after personal foul, and then there was a first down, and I mean, they must have had like 10 plays, like right there between the 10 and the 1. And so one of you guys that don't know football, this is an easy thing to understand, but once you get too close to the goal line, certain penalties, right, have certain yardage attached to them, like 5 yards, 10 yards. But if you get too close to the goal line, well, they can't give you the 5 or the 10 because it puts you in the end zone. So what they do is they cut all the penalties half the distance to the goal, right? So my dad calls me and he's like, hey, so I mean, in theory, you know, how many times can you do that? Like, is there a limit? And I was like, no, it can go on forever. You're literally describing one of the most famous mathematical sequence or series in all of math. And I was like, the reason they cut it half the distance to the goal is because you can cut something in half forever in theory without ever running out of stuff, okay? So one of the ways we can see that is let's look at a 1 by 1 square, right? So if I want half of this area, right? Well, we can see right? So there's my 1/2. And then I want to add a 1/4 to it. So I cut the remaining half in half again. And we'll shade that in. Then if I want 1/8 of my area, I just cut the remaining 1/4 in half again. All right, and then you can see we want a 1/16. We would do it again. So you can kind of see where this is going, right? Every new fraction, I'm just going to take half of the leftover area, and then half of the leftover area, and then half of the leftover area. It's never going to exceed 1. I'm never going to run out of room. I'm never going to run out of stuff. And so we can see here that the sum from 1/2, right, to infinity of 1/2 to the n is simply going to add up to the value 1. Right? Now, right, we can see here that this is why this works in football, because you can keep cutting your remaining yardage in half and you're never ever going to get there, okay? So there's also another version of this sequence which we can start counting from 0 to infinity. So if I index it from 0 rather than 1, what's the first term going to be then? 1/2 to the 0. 1, right? And then when I start at 1, I'd start with the 1/2. So if we were to set up the same series and count from 0 to infinity, we would see that it adds up to 2, because you get that 1 extra term, which would be 1. So there's a really stupid math joke that no one ever gets until you've seen this sequence, but it's of a line of mathematicians walk into a bar, and the first guy walks up and says, "Can I have a pint, please?" And then the second guy walks up and said, "Can I have half a pint?" So the bartender goes over, fills 2 pints of beer, and sets it on the table and says, "You assholes work this out," right? Because he knows what they're all about to do to him. So, so that's yeah, dumb math nerd joke, right? If I know them, I'm going to torture you with them too. All right. So let's look at another way we can show that this is summing up to 1 more mathematically. So we said that when you see a sequence that you've never really seen before and you're not really sure what's going on, we look at the partial sums, okay? And that's a really weird idea for a lot of people. I didn't really understand it too well when I was doing this. I saw what partial sums meant. I was like, yeah, I get it. You're just adding up this many terms. But it was formulating the sequence of partial sums that kind of threw me for a loop. But let's do it with something kind of simple that we all know how to work with. So if I wanted to show that this guy is summing to 1, the other way I can do it is I can look at its partial sums. So we're still summing from 1 to infinity. And if I look at the first partial sum, right, I just get 1/2. But if I look at the second partial sum, right, I'm adding the first 2 terms, and 1/2 plus 1/4 adds up to 3/4. And then I'll grab the third one, and I already know the third one's going to be A1 plus A2 plus A3, so I'm just going to grab the sum of the first 2 and add the third one to it. Because that's all these do. You just keep adding the next term to the previous term, okay? So now what I'm supposed to do here is I'm supposed to see if I see any kind of pattern emerging. And if I see a pattern emerging, then I might be able to come up with a formula for the nth partial sum. So our sequence of partial sums, right, is 1/2, 3/4, 7/8. So just like we ended class with on Thursday, well, if I look at these numbers, can I write an expression for the pattern that I see emerging? So hopefully the denominator's pretty easy, right? Everybody can kind of see what's happening in the denominator. You're going 2, 4, 8. Obviously, next one's going to be 16. The denominators are simply counting up in powers of 2. And because we're starting with n equals 1, I need to make sure that my exponent has the correct number. So if I put in n equals 1, I will in fact get 2 first, and then 4, and then 8. So I don't need to make any adjustments. All right, now what's happening to the numerator? It's what? It's 2 to the n minus 1. The numerator is 1 value smaller than the denominator. So if the denominators are counting up by 2 to the n, the numerator is 2 to the n minus 1. Right? 1 is 1 less than 2, 3 is 1 less than 4, 7. So I actually know the next number in the sequence is going to be 15 over 16. Right? And then I'd get 32 over, or 31 over 32, right? So you just know your powers of 2 and subtract 1. So this is what we mean by when we say look at the partial sums, right? So now we have a sequence of this. If I take the limit of this and it converges, well then the series will converge. If I take the limit of this and it diverges, the series will diverge, right? More importantly, whatever the value of this limit is, that's the sum of the series because I'm summing up the nth term, right, as we go to infinity. So if we look at this, we can see this is an infinity over infinity situation, and the derivative of the numerator is 2 to the n natural log of 2. The derivative of the denominator is also 2 to the n natural log of 2, and so we can see that's just going to become 1. And so the series converges to 1. And we knew that that's what should happen because we were able to look at it geometrically and see that we were never going to run out of area in that square. So therefore, it should just all be locked in 1. All right, now I want to make a note too. This unit, more than anything else, and this is going to be really common in math and stuff going forward, it's not always going to be able for you guys to always really fully get what's going on in real time. So, you know, get the notes down. I try to keep things organized for you guys, you know, get it the best you can, and then you're supposed to go home, look over it, let it sit with you for a minute. But it's really, really hard. I mean, the days of just walking into class and being like, oh, I got what we did today and I can do, that's not the way it works anymore. So this stuff takes a little minute to kind of wrap your head around. It's a lot of you have never done anything like this before. I struggle with this when I was learning it, but it is all doable. So are there any questions about this before I show you another series? Yeah. Where did I get the what? So the derivative of 2 to the n is 2 to the n natural log of 2. We talked about that last week. So it's like the derivative of a to the x is a to the x natural log of a. So it's kind of an obscure derivative that you don't use a lot in Calc 1, but we use it a lot in sequences and series because we have a lot of exponential functions that we deal with. Yeah. And if you think about it, everybody knows the derivative of e to the x is e to the x. Well, it's really e to the x natural log of e. It's just natural log of e is 1. So that's why it just comes back as e to the x. Okay. All right. So we're going to talk about types of series like that, like this in a little bit, but I just want you to make a note here that the type of series we just looked at is called a geometric series. So we're actually going to do a little bit more stuff with geometric series later, but this is a famous type of series, all right? And so we'll revisit that in a minute. So let's look at another type of sequence or series. And these you're going to see, just like with sequences, can take lots of different forms. So let's see what's going on here. So I always recommend, in the early kind of days of working with series, I always recommend, you know, it doesn't hurt to just list the first few terms out. Just get a look at them, just see what they look like, just familiarize it. And after you've worked with several of these, then you're actually able to see more in the formula what's going on. But I think listing out the real numbers is quite helpful. So if I sorry. So if we look at the nth term here, we can see that these are just the difference of 2 fractions. So if I plug in n equals 1, well, I'm going to get 1 over 1 minus 1/2. That's the first term. Then when I plug in n equals 2, I'm going to get 1/2 minus 1/3. And I'm going to go out one more. And just like on the last one, I'm going to cheat and tell you that this does in fact sum up to this. And I'm going to show you how we get there. So if you look at these terms, you should definitely see a pattern emerging. We've got 1 minus 1/2, and then the very next term has a positive 1/2. And remember, at the end of the day, we're just adding all these up. So this negative 1/2 is going to cancel that positive 1/2. And then the negative 1/3 we created here will get immediately wiped out by the positive 1/3 in the next term. You can see what's happening. So what we've got here is the 1 is still here. And then when you get to the nth term, right, which is this guy, the 1 over n should be canceled out by the previous term you created, because that's what we can see happening. So what's going to happen with this series is all the intermediary terms are going to cancel, and you're only going to end up with the first term and the last term. And we actually have a name for a series like this. This is called a telescoping series. So if you think about the old school little collapsible telescopes you'd see on like ships and stuff, right? They fold up, and that's kind of where this name comes from. right? The first term on the series, which could be the lens of the eyepiece, right? And then the last term of the series, which could be the other lens on the other end, right? They're the only two things you end up with because all the terms in between cancel each other out and collapse back. This one was really obvious because it just canceled one back. But sometimes we can create telescoping series where you see the terms are canceling a couple back. But that's what a telescoping series is that all the intermediary terms, or most of them, collapse down. So, if we look at the nth partial sum, right? Well, you're going to have the first term, and then all these pieces get wiped out, right? And then when you get to the nth term, this guy got canceled out from the term that was created previous. So all you end up being left with is the first term and the last piece of the last term. Does anybody not see that? Okay. So on a telescoping series, it's kind of easy to come up with the nth partial sum. If you can, what you're looking for in a telescoping is you want to go, well, what's the pattern of the things that are going away? So you can remove them and you only deal with what's left. So if we look at the limit here, well, the limit of 1 is just going to be 1, and the limit as n goes to infinity of 1 over n plus 1 is 0. So this thing just sums to 1. Now this is not the only telescoping series. There are different types. But this is just one example of one. Okay? All right, so let's look at another series. So this guy is literally this. Just every term is 1. It's like when kids are learning to count, they always try to count to infinity. I used to try to do that. And then you just like torture them. And then just whatever the biggest number they can think of, you just add 1 to it. And just like makes them crazy. All right. So, yeah, little kids don't understand the concept of infinity at all. It's really funny. All right. So here, we're just literally, we get 1. The second partial sum would be 2. The third partial sum would be 3. Right? So the partial sums are just going to be n. Right? So if you add up 1 1, you get 1. If you add up 2 1s, you're going to get 2. If you add up 3 1s, you get 3. So the partial sums would just be this. So what's the limit of that as n goes to infinity? Infinity. So this thing sums up to infinity. We can also show it, right, by looking at the limit of its partial sums. So this guy diverges. More importantly, we said at the very, very beginning that no series can converge if the limit of its initial term isn't 0. Well, the limit of that term is not 0. The limit of that term is 1. So you're just basically going to be adding up a bunch of 1s at some point. So therefore, you cannot converge. Okay, so we also could have shut it down right then. All right, let's look at another series. Oops. So the limit of that nth term is in fact 0. So we have a shot at convergence. I could start listing out these terms, but I want to show you this one as an example of that, and like I said, we're going to do a lot of stuff moving forward. This is just an introductory in the series. But I want to show you this one to show you that sometimes we need to rewrite things to make them look more familiar, because this is actually a telescoping series, right? So one thing is, if you look at the denominator, that's not 4, you know, it's not an exponential. That's actually 4n squared. When I look at the denominator, what I see is a difference of squares. I have 2n squared minus 1 squared, basically. So I can factor the denominator. And these factors make me suspicious, okay? So the reason I'm getting suspicious is because, well, if I plug in 2n plus 1, and then I plug in 2n minus 1, well, if you think about that, those numbers on a number line, they're only 2 spaces apart, right? And I know that we have a thing we learned called partial fractions, right? I can split this up to be either the sum or the difference of 2 fractions. And I might have a telescoping series here because that stuff in the denominator is really, really close. And if n is 1, right, this term on the left just becomes 3. If n is 1 here, this term becomes 1. And if I'm in a situation where I'm wiping stuff out and it's telescoping, it's really easy to find the sum. So we know that using partial fractions, we could rewrite it like that. And if b turns out to be a negative number, I'm going to be adding and subtracting stuff. It's very possible I have a telescoping series. So using partial fractions, I'll get that a is 1 and b is negative 1. So now my series is this. So if I start listing out terms, oh, sorry guys, this should be the minus, this should be the plus case. So a should be negative 1, b should be positive 1. And so now when I list out the terms, I get this guy. So I also knew that 2n minus 1 and 2n plus 1, I also knew I recognized in those factors that those are odd numbers. Because that's how you write an odd number, right? If it's an even number, we write it as it's divisible by 2. So it would have been like 2n, would have told me it's even. But when you add 1 to an even number, you get an odd number. So that's exactly what I got. I got odd numbers in the denominator, and those odd numbers were 1 apart from the number line, or 2 spaces if you want to think whole units. And so we can see that the negative 1/2, or negative 1/3, excuse me, cancels with the positive 1/3. The negative 1/5 cancels with the positive 1/5. So this was, in fact, a telescoping series. So if I look at my nth partial sum, it's 1 minus 1 over 2n plus 1. So the 1 is there because the initial term stayed. Everything else cancels, and this term would get canceled out by the previous term that I generated. So I'm only left with these two guys. So the limit of this is just going to be 1. And so this series, right, converges to 1. And this is another example of a telescoping series. Now, we're not going to use partial sums. We're not going to use them to calculate a lot of our series, because you'll see very, very quickly that the partial sums and coming up with a sequence of that and trying to find that nth term is, in some cases, practically impossible because there's no discernible pattern. So what we're going to do moving forward is we're now going to start to investigate different types of series, and you're going to see there's lots and lots of different tests we can apply to test whether a series converges or diverges. But within the series, there are certain tells that emerge that kind of tell you which path you kind of need to go on. So each technique usually involves some either kind of limit or algebra tool, and you'll see it specifically works well with certain types of sequences and series. So these kind of first two that we looked at, a telescoping and geometric, are pretty much the only ones where we can actually get an actual sum out of them. Other series, we know they sum up to something, but it's just not quite so easy, or the tools needed to do that is just beyond the scope of this class. So, but the first thing we're going to investigate now is we're going to talk about geometric series, because when you see one of these series that we know how it behaves, you get really excited because they're really easy to work with. And so we probably won't finish geometric today. We'll get started and then we'll finish it up tomorrow. All right, but let's talk about the geometric series. And the geometric series, what's cool about it is like you can literally use geometry to visually show what these things sum up to. So with me doing the 1/2 example, that was an easy one. We could square and a half, but I could take a third, a fourth. It's just the pictures get a little bit more complicated when you're trying to divide things up. All right, so the form of a geometric series notice this time I'm starting from 0. Be careful to always pay attention to your indices. Is sum A, that's a coefficient, times R raised to the n. A cannot be 0, otherwise you're just summing a bunch of zeros. And your R value, the absolute value of R, needs to be between 0 and 1. So essentially we're getting a fraction, right? But that fraction can be positive or negative. That's why we said the absolute value. So we already said if you take a number bigger than 1 and raise it to the n, right, it grows, it gets bigger, right? But if you take something smaller to the n, than 1 and raise it to the n, it's going to get smaller. So by looking at partial sums, if we sum from 1 to infinity, we can find a discernible pattern, and we actually just did that. We did that earlier where we saw, oh, it was 2 to the n minus 1 over n. However, when you sum from 0, that first term of 1 would violate the rest of the pattern that you're seeing in the rest of the partial sums. So we actually don't really use partial sums. We sort of do in order to prove that what I'm about to show you is true. But there's actually a known formula for this. And the known formula is that this series will sum up to A over 1 minus R. So using partial sums, I can prove this to you. And once we see where this comes from, then we just get to use it, okay? So if you look at the nth partial sum of this series, you're going to get A plus A times R plus AR squared all the way up to A times R to the n minus 1. Now, note on this, we started counting from 0. So the first term was R to the 0, and that's why you just get 1, or A out, right? Or just whatever the coefficient was. So this power right here, right? Some of you may have thought, well, it should be n. It's 1 back because we started from 0. So remember what partial sum means. It means you're summing up the first n terms. So from here to here, these are n minus 1 terms, and when you plug back in the 0 part, that gave you the nth term. So everything got shifted back by 1 because we started from 0. All right? Then let's take this same equation and let's multiply both sides by r. So if I multiply the left side by r, well, what's going to happen is when I distribute the r among this rule, it's going to up the exponent by 1 in every single term, right? So this a is now a to the r. A to the r is now ar squared, right? Because I'm multiplying every single one of these terms by an r. Right? Then what I'm allowed to do is I can say, well, I can subtract one of these equations from the other. So I'm going to take the top line and I'm going to subtract the bottom line. So on the left, you just get s sub n minus r times s sub n. But on the top, look what happens. This a sub r, right, cancels that a sub r. And this ar squared cancels that ar squared. And then the ar cubed would get canceled, right, because of the next term. And then this ar to the n minus 1, right, would get canceled by this guy right here. So all you're left with is a minus a times r to the n. So just like with the telescoping series, because we had so many terms repeated, all the middle stuff was getting wiped out. So then I can factor out the a. So on the left, if I factor out my s sub n, I have s sub n times 1 minus r equals a times 1 minus r to the n. And then we want to solve this for the partial sum. So the partial sum is a times 1 minus r to the n over 1 minus r. But if you notice in the original formula, that stuff wasn't there, right? So where does it go? Well, if we take the limit of the nth sum as n goes to infinity, well, a over 1 minus r is just a constant. So that's going to come back as itself. Well, what's the limit of this stuff going to be? Think about what the condition on r was before you answer. R had to be a special thing. Well, it's not quite 0. The limit of r to the n is 0. So the limit of this just becomes 1, right? So remember, r had to be a number less than 1. So if you take a number less than 1, like if that were 1/2, right, and we had 1/2 to the n, we know that that limit would go to 0. So what happens, this piece right here goes to 0, and so you just end up with a over 1 minus r. Okay, so this is actually a really good place to stop. When we come back tomorrow, we'll do a bunch of examples, and then I'll show you all the useful stuff you can do with the geometric series.